Good afternoon, ladies and gentlemen. My name is Chiravachradej. We meet again for the statics lecture. Today we look at another structure. It is a structure that involves the use of cables. So far what we have looked at the internal forces are the rigid jointed frame, or sometimes we look at it as one-dimensional element like beams, like columns. We also have looked at the structure where all connection is a pin type, which we call the pin joint trusses. Now, this is another system of how we create a structure to resist the weight. Okay? Usually, well, the cable itself have in many use, but in the view of civil engineering, we're looking at it in terms of how we actually help the structure carry the loads. Right? Well, the topic for today is cables accepting just point loads, series of point load, of course, or maybe it could be a single point load. However, this is just the introduction to a more complex system of the use of cable. Right? So we actually look at something like, we are talking about the bridges that stay with the cable helping to take some loads, okay? Which we actually call cable stay bridges. Could be suspension bridges, could be, for example, that. This is probably the kind of like the earliest models. Notice that the structure now has a tower and has the road on the pavement. The span of the bridge is very, very long. Okay, it's across a cliff. Now, if the span is long, I mean, we have done this bending moment diagram before. We know that even though the load is the same, but if the span is longer, the bending moment value become much higher. At one point, when it becomes so high, then the cross section or the material we use will be so large, which is sometimes not really appropriate or too expensive, or sometimes up to the point that, well, you know, let's find another way to do it. But in this case, what we do is we use cable to help resist, reducing the diffraction and also reducing the transfer the load from the beam to some other part as well. Basically, we will talk about this later. This is, I think, the Golden Gate Bridge in San Francisco, I think. I'm not too sure. But again, notice the span is really long. Of course, without the help of the cable, the diffraction will be so large. Okay? So that's why we use a cable to pull up the slab or the floor so that it doesn't actually deflect so much. Okay? Another one. The same idea. The span is long, then reduce. Notice the girder, the beam girder is still really big, really deep though. Okay? Okay, so this kind of bridges does deploy cables to help reducing the need of the huge cross section, basically to reduce material, whereas it still have the safety precaution and of course the usability still. And there we are. The schematic is this. So we have the series of the structure, right? You have the normal beam going across. We have the column, the footing, okay, the deck, or well, the floor, the deck, or the roadway going across. Okay, we have the anchor box. Now the cable system on the top there will be the one that is on the main. The main cable is the one that go on the top. Okay, connecting like the framework of the load transfer. Whereas if we look at the more detail, the one that is vertical, the vertical cable, sometimes called suspenders, sometimes called secondary cable or vertical cables. Okay, so the idea is that rather than all the weight going down to the two anchor and the two foundations alone, only for the two foundations alone, they actually go straight upwards to the cable first, and you see the system of load transfer. Then the main cable take this load and then pull into the anchorage there. Okay, so basically it's a kind of rather than having only the sideways load transfer from the from the load weight to the foundation, then actually some part will go up, some part will go still sideways, some part go up and then go down to anchorage where it's been pulled up per se by the anchorage. Okay, so that's the way we set up the system of the load transfer. Now, this is a complex system. Okay, so to understand this and to see the picture, then we will actually look at the cable in a series of complexities, or in fact from simplified version to the complex version. Okay, so we will start off looking at the cable system, which is today, okay, that only accepted the point load, or sometimes we call concentrated loads. Okay, then next time we'll move on to the cable subject to distributed load. Okay, we will talk about detail then, and then the last one is the cable subjected to its own weight, to self-weight. Okay? Usually in real cable, then it will combine between the second and the third. Okay? Now, as I said, today will be just the beginning of our understanding on how the bigger picture works. The weight that hanging onto the main cable, they are very rare in real life working. However, there are some like for example, the carriage going through from cliff to cliff, right? However, again, and the last topic, cable subject to self-weight, that will be a section that I will require your own reading. Okay, we will talk with detail when it's the end of the second series, the one in the middle. Okay, we'll talk about it then. Well, now, when we talk about the cable subject to a point load, how would we see a picture? It's usually like this. There will be two supports, okay, on either side. Then we have serial cables with certain point loads coming down at a point. When we start off here, just to simplify things, and well, in fact, mostly it can be said so. If in this case, we will say that the cable, maybe we can call it a rope, or cable system, the cable itself is very light compared to the weight pulling it down, and therefore we kind of ignore it, okay, because it's so small. And plus, if it's small enough, then this line, the cable line, will be so in a really high tension, and it becomes just a straight line. If we consider self-weight, then it should have an arc. No matter how small, it's still an arc. So if we think this is assuming for the sake of calculation and for the simplicity of it, then we could say that the weight is so small that we don't have to actually take into account of the cable, of course, the weight will have to. Okay. Now, if we look at this picture, apparently we should realize one thing though. The system of calculation, that all of the conditions of the force system is something that we already know. Okay, so basically it has the pin support on both sides. Then each support will have two reactions, as we already know. The pin joint in each circle, A, B, C, and D, those are pin joint connection, pin type connections. Okay, meaning then at point B and at point C, the cable can rotate freely. Okay, there is no resistance to that change in angle. Okay. Plus, then this is a cable system. The black line here is not a beam. It's not a rigid structure. The thick line connecting AB, BC, and CD are just cable ropes. Okay. So basically, again, it will take. We already know that. We talked it in the first half. Is that this cable will take only tension, and it is being tension and being what we discussed before, then this kind of axial force then will have to be on the same line as the cable itself, meaning if we know the angle of the cable, then we can also tell the angle or the forces, the internal forces, the tension. Now, before we keep carrying on, but as I mentioned, everything we actually need to calculate this picture, this equilibrium, from external forces to internal forces, we have the information to do it. We have all the information to do it. It's how we arrange this knowledge and this skill into solving it. Okay. So let's see what we should move on. Okay. So as usual, talking about forces, talking about equilibrium, then we talk about free body diagram. Start off, I would draw the total free body diagram. Okay. This is just the body, right? From A to B to C to D. The whole body. From one support to another. No support, free body doesn't have support. Then the two action forces, right? The point loads that we were talking about. And of course, at point A, then we have the tension there. So here we are with the free body diagrams. There. So this is just the body from A to D, right? Point A, point B, point C. This is the whole body. Then we have the two action force, the 18 kilonewtons, and the 30 kilonewtons. Then, of course, at point A, we have the pin support, two reactions there. At point D, we have also two pin support, we have two reactions there as well. Now, at this moment in time, we have one free body diagram. Then we have three equations, correct? We have sigma fx equal to three equations of equilibrium, that is. We have sigma fx equal to 0. We have summation of all forces in the y direction, sigma fy equal to 0. We have the summation of all moments about any point equal to 0, or sigma m equal to 0, right? Three equations, but we have four unknowns, right? Well, here's the hint again. At this part of your study, at this part of your learning curve, we are not going to have more unknowns than equations. It's just you have to figure out other free body diagram to help out, right? Similar to the structure with the pin connection, something like that, right? So basically, if we really think about it, we have, this is kind of like the joint, if we look at it as a truss, because it's, right, it seems to be like the same as the truss idea. We have all connection are pins, right? All load is at the joint, not on the member. So the idea is similar to truss. So basically, if we use the same idea of thinking, then we have four joints. Each joint have two equations. We have overall 8 equations, right? The unknowns, we already have 4 unknowns here, the all reactions. We also have 3 tensions, right? So become 7. And we have h, we don't know, or basically the angle at point D, of the rope at point D, the same, okay? So we have 8 equations, and we count 4 reactions, 3 internal forces, 3 tensions, 7. Then we have one more height, or in fact the angle, so 8. So 8 equations, 8 unknowns, we should be able to solve it. Well, for example, in this case, I can actually show this picture, right? If we draw joint A, then we see that, right? The RA, XRAY, and then we have the TAB. So if we recount the two pictures together, right? Now this time it's not using the truss idea, using the free body diagram idea, okay? The left-hand side, you have 1, 2, 3, 4 unknowns, plus H is one more, right? So 5 unknowns, right? Correct? Then we have on the left-hand side, RAX, RAY are the same RAX and RAY, both pictures, so we don't count them again. We have TAB. So we have 6 unknowns. Oh, sorry, H is not involved, sorry. 4 unknowns on the right-hand side picture, correct? And then the RAX, RAY, RDX, RDY, all reactions. Then we have TAB, right? TAB, we have the angle, okay? Because the height is 2 meters, the AB. Don't forget, TAB will be on the same line as AB, right? So the AB, we have the height of 2 meters, and then we have the length of 2 meters on the cable AB. Therefore, the angle is 45. Now, then, if that cable AB this way, sorry, AB this way is 45, then TAB must also be 45. So we know that angle, okay? H is not involved here yet, anyway. So basically, in these two pictures, we have 5 unknowns, okay? On the right-hand side, we have three equations, sigma fx, sigma fy, sigma moment, right? Then on the left hand side, however, we don't have we have three equations, but sigma moment is always 0 because it's just a point. So you have 0 equal to 0, which although you still have the equilibrium of the rotation, but you cannot, the equation is not useful, it's not aiding us in our calculation. This is like a joint, a point. Therefore, it's a kind of particle type. In effect, we have only two equations. The summation of force in the x direction, in the y direction, right? So, 3 equations, 2 equations, 5 equations. 4 unknowns, 1 more unknowns, 5 unknowns. 5 equations, 5 unknowns, then we should be able to sort it out. Okay? So, let's see how. Then, now, once we finish with the free body diagram, then we start thinking about how to calculate them. Okay? I don't think the left-hand side picture is a good place to start. It seems to have so many unknowns. In this case, maybe we should start with this picture, because if I take moment at point A, then RAX times 0, RAY times 0, and RDX also on the same line, also times 0, correct? So only one unknown. The same, I can take moment at point D, okay? And only RAX only RAY shall appear in my equation. There we are. So I take moment at about point D as equation 1. Then I have RAY, sorry. Okay? Then once I get RAY, then I should be able to figure out what RDY is, right? Sigma Fy equals 0. Okay? Or you can do sigma MA now equal to 0 to find RDY. Other way is fine. And there we are. Then we can find RDY. Now, RAX and RDX, well, it's not, that one is not quite helpful yet. However, if we look at the left-hand side picture now, okay, now we know RDY and RAY, correct? If I know RAY, actually I should be able to calculate TAB using the sigma, the summation of all forces in the y direction, sigma Fy equal to 0, right? So, using that equation, don't forget, I repeat myself, RAY and TAB, RAY we already know, okay? So, then we can calculate TAB. Now, if I can calculate TAB, using the same picture on the left-hand side, then I can calculate RAX, right? Sigma Fx equals 0. Here we are. There. Oh, we know TAB, so we have RAX. Now, if we know RAX, come back to the free body diagram on the right-hand side, the big picture. Then I can use sigma Fx here and find RAX. Sorry, too quick. So, we know RAX, then we can find RDX, right? Because they must cancel out, become 0. Okay? Now, let's update what we have here then, shall we? Then, update the free body. We know all the external forces, meaning the action and the reactions on the supports. Now, we also have one tension, that TAB, right? So, let's mark it down. Now, if we want to know some other things, then we keep working on it, okay? Let's go for TCD. Don't forget, we don't know theta because we don't know the height, we just know the width, right? But in that picture, if we look at joint D, this is kind of like a joint method in thrust analysis, right? So we have two knowns, we have two unknowns, TCD and the angle, right? So we have it's a point, the joint has two equations. Then two unknowns equation, well, can be solved. There we are. We use sigma Fx, we have sigma Fy. Well, by the setting, then we can find the angle using tangent, and we can find TCD taking advantage of sine square plus cosine square equal to 1. Okay, so there we are. At first, it should be sine over cos. Okay, it should be 8 over 7, but maybe 7 over 8 and then take it over. Okay, then we can work out with tangent. Then we work out the theta. Okay. Again, this one here, so that we can take advantage of sine square plus cosine square equal to 1. Just in case that maybe we calculate theta wrong, but at least we got t correct. Okay, there we are. And therefore we can work out TCD. Okay, so we have theta, we have TCD, then update the free body diagram maybe. We have the angle. Then we have one more to go. We have T tension BC and the height H that we have to identify. But with the triangle, we know that part, we know the angle, then we can work out, the angle of CD, that one, CD and that 90-degree triangle. Okay, so we can work out H. There, using the triangle, the picture. Now, if we know that H over I, H over 1 meter will be the value of the tangent, right? Therefore, we can work out H equal to 1.824 meter. Now we have TBC left to go, right? Now, again, before we start, then we need to find out the angle. Okay, in this case, I will measure it with BC and the horizontal line, call it alpha. But we know H, right? Which is from the level of AD to joint C. And I know the level from horizontal level to joint B. So I have the height, that gap, which is 2 minus, of course, the whole height, minus 1.824. That is the value. And if I know that value, I know the base, 3 meter, then I can work out alpha. Okay, very small, but then it still have effect on the force. Once I have that, then I can look at the equilibrium of joint B. Right? Again, TBC will be on the same angle. Okay. Once we have that, then normal calculation, sigma of x, and then sigma of y, then we get the check. And of course, if we carry on doing joint C, that will provide us with two more checks, the same as the pin joint truss. Okay, but this is the answer we want, so this is the answer we supply. Okay, well, the complexity of the cable is that it is not really the new knowledge as such, at least at this part. It is something we already know, as I said, but it's just to solve it, we have to have a better understanding of how we deploy our free body diagram. Okay, and it's again basing the idea on the a more complex topic later on. One thing though I will mention here, if you notice, every time we take the force component in the cable into the horizontal level, on the horizontal line, right? In this case we call X usually, it always comes to the same number, which is in this case 17 kilonewton. And in all other example on this type of calculation, it will always come down to one number, maybe not 17. It's just a number per application. Okay. Now we're going to look at another example. This time here it's a little bit more complex. Oh, sorry, joint C, as I said. Then, okay, sigma of x, then 0. Notice, if it's x, you will have recurring number, 1717, all the time. Right, sigma of y, then check. Okay, then once we calculate them all, we check whether it should be all right, then we are ready to answer. TCD is also tension, and why do we have two TCD? Sorry. That's probably the typing mistake. Okay, so those are all the answers. 8 answers in all 4 reactions, 3 tensions, and 1 height. Okay. Now let's go there. Okay. Now this is similar problem. I have to say similar because it's not the same. I think I forgot to explain something. Oh no, it's okay. Okay, yeah. It's a similar problem. The difference is that you have two different levels of support. Okay, it makes the calculation a little bit more. The idea is the same. The calculation is a little bit more complex. A little bit more longer, and the way we look at it is has variation on how we look at it. Okay, that the free body diagram. Again, for unknowns. Okay, one free body diagram, three equilibrium equations, right? The same thing. Maybe we can solve that, adding that. The same system here, okay? So then again, we have 5 unknowns, okay? 5 unknowns. Notice if we look at the big picture on the right hand side, the value h does not get involved yet. It will later on in the calculation, because we know if we take moment at point A, the gap is 1 meter. If we calculate at point D, the gap is still 1 meter, right? So we don't actually need h to start off with, but we will need it later on. Okay, so in this case, then we could do the same thing then, because as I said, 5 equations, 5 unknowns. So there we are. Take moment of point D. Then we have equation 1. Then go to that side. Well, you can pick it up. However, you can go in any sequence if you want. However, since I see that equation and I realize that I have AY and RAX in the equation, so maybe if I can pair RAX and RAY, then maybe I can solve RAX and RAY before we move on. Okay, to get more equations. So just focus on the task at hand. Then going there, I have RAX, and there I have RAY. The linkage between RAX and RAY apparently through TAB, right? So therefore, I can use equation 2 divided by equation 3. Then I get RAX and RAY are the same. Okay. Because TAB and TAB disappear, sine 45 and cosine 45 is the same, so I can take it out, then move RAY into the other side. I have RAX equal to RAY. Now notice equation 1 and equation 4. It has 2 equations. We have 2 equations here, and we also have 2 same unknowns, RAX, RAY. So we're going to solve it from then. Okay. If I substitute equation 4 into equation 1, then I get the value of RAY. Once I have value of RAY, then I can have value of RAX. Now, before we move on, as I mentioned before, when we take component in the x direction, we tend to have the same number tend to pop up. We're going to prove it later in the next lecture, of course, not this lecture. However, notice that in this problem then, last time it was 17, right? This time here in this example, the number 20.4 will keep popping up when we do sigma, when we do the component of the force in the x direction, horizontal line. Okay. Anyway, then look at the right hand side picture. Then we know RAX, we know RAY, correct? Now, with that right-hand side picture, we just use sigma moment so far, so we still have sigma fx, sigma fy to be used. Therefore, we have 2 more equations to go with 2 more unknowns left. Therefore, we should be able to solve it straightforward. Sigma fx, then dx, again 20.4. Sigma fy, well, could be anything else. Okay, so we have all the reactions, all the unknowns in these 2 pictures. Let's update it. And of course, we can go through the system to find something else. Okay, so notice that then we have everything else. Then we can go through the joint method like last time, go through joint to joint, and we find everything else. Now, however, this is not the only approach we have. We can look at it at a different way, in fact. So I will give example. Okay, let's start with this. We have RAX, RAY, RDX, RDY. 4 unknowns, 3 equations. We don't want to look at joint A for some reason. Okay? Well, so what do we do? Okay? Maybe we look at another body altogether. For example, like this. Basically, rather than using joint A, this time I look at 2 of them. One is from A to D. This is the body, the first body we look at. Then we cut from B, C, and D. Okay, not at joint A. Now, notice that if we look at this, then at least it still share. Okay, the amount of unknowns. We have 4, and then we have 5 unknowns. Yeah. The equation, we however have more. This time we have 6 equations. Nevertheless, we should be able to solve it out. In this case, when we set it up this way, well, it's almost as if we are not solving it to RAX, RAY anymore. This one here, we're solving it to, of course, RDX, RDY. Okay, so here we are. Then I can take moment about point A on the right-hand side picture, taking moment about point B on the left-hand side picture. Then I will have relationship between 2 relationship between RDX and RDY. Okay, there we go. As I said, 6 equations, 5 unknowns. Then that one, I can take sigma moment here, then sorting out, then I have a pair between the x, dy. On the left hand side, then I can actually take moment about point B, then I have another pair of relationship between RDX, RDY, and of course, in this case, we can have 2 equations, 2 unknowns again, sort it out. There. Again, it's the same as last time. And again, when we talk about horizontal line, we have 20.4 kilonewtons. Then once we know that, we can move on and solve the rest. RAX, RAY, and of course, TAB, if we want. Oh, we don't even need TAB, because this time the question doesn't ask for it. It asks for just reactions. Okay? So, this is the first step. Again, I repeat myself, this is the first step for a more complex system in cable, resisting forces and taking some loads of the main structure. Okay. The trick of this topic, not the trick, it is really the understanding you need, the expertise you need, is on how to see the free body diagram, how to be able to see the path of your calculation before you actually calculate it. Okay? So, this is a good practice for anyone that need to keep doing mechanics study or work on mechanics. The word mechanics means force and movement, or force and without movement, whatever. Okay? But anyway, so that should conclude the lesson for today. And I shall see you guys again for the next lecture. Thank you very much.